Hi, in this video we will find a criteria for a matrix to be diagonalizable. The focus will be on eigenvectors and you will see how that will give us that criteria. Well, first thing to recall is that we saw already that if A is diagonalizable, the eigenvalues of A will appear in that diagonal matrix. Then A is going to be similar to diagonal matrix where the entries on the main diagonal are the eigenvalues. So eigenvalues of A will appear there. How about eigenvectors? Is there anywhere, can we see eigenvectors anywhere in this computations? Well, if we continue these conditions here, you see, A is similar to that means what? It means that there exists an invertible matrix. P. Well, I will write this P as columns, so P1 up to Pn, column 1, column 2 up to, such that, well, P inverse A, P is equal to that diagonal matrix lambda 1 up to lambda n. Well, remember that we had another equivalent version that this, I can put it here. That is equivalent way of saying that this is similar to that. Okay, nice. Well, now if you write the column version of P, so P1 up to Pn, and here P1 up to Pn, you multiply it to lambda 1 up to lambda n, 0 here, 0 there. Then if you multiply, well, each column, you can get each column by AP1 will give you the first column, AP2 will give you the second, and APN will give you the nth one. If you multiply P to this diagonal matrix, what you will find will be lambda 1 P1, lambda 2 P2, and lambda n Pn. So we have two matrices which are equal, so then the corresponding columns will be the same. So A P1 needs to be equal to lambda P1. And AP2 is equal to lambda, this lambda 1. So lambda 2 P2. And APN is going to be lambda NPN? Well, what does this mean? This means that Pi, the ith column of that invertible matrix, is an eigenvector of the matrix A corresponding to lambda I, the eigenvalue lambda I. Exactly in the same order you put them in the columns. But you have to note that P is invertible. Since P is invertible, so all its columns are going to be linearly independent. So then this means that P1 up to Pn are linearly independent eigenvectors of A. So if A is diagonalizable, then A has n eigenvectors. It has n eigenvectors which are linearly independent. So that's something that we just saw. But interesting thing is that this is not very difficult. You can read it from the book now, that this is if and only if. So I can just get rid of that n and write if and only if. Means that if A has n eigenvectors which form a linearly independent set, A will be diagonalizable, and the other way around. Yeah? But the important thing here is that we already saw, not only we got a criteria, just check, find all the eigenvectors and see if you have enough eigenvectors to form a basis, linearly independent, and they will have n eigen vector. If you have enough of them, then you know that it is diagonalizable. But then you can go ahead and form that matrix, invertible matrix P. What is that? Put the first eigenvalue, second eigenvalue up to n eigenvalue in the diagonal matrix, and put the eigenvectors in the first column, second column, and so on. That will form your P and D. Okay, so let's do an example for this. You will see how this, what I mean by this, will help us to find those entries. So here we have matrix A, 1, 0 is diagonalizable. We will just check, we will check it and show that it is diagonalizable. And find invertible matrix P and a diagonal matrix D such that P inverse A P is equal to D. Well, first find eigenvalues of A, which is 1, 0, 1, 0. You see, this is upper triangular matrix, and the upper triangular matrix has eigenvalues equal to entries on the main diagonal. So it will have two eigenvalues. Lambda 1 is equal to 1, and lambda 2 equals to 0. Very nice. Right away, we have the diagonal matrix 1, 0, 0, 0. How about the invertible matrix P? Well, let's see the eigenvectors of this guy. Vectors of lambda 1. So for that, we have to solve this A minus 1 times identity 0. And it will give us what? It's 1 minus 1, 0, 1, 0 minus 1, 0, 0. And well, this is the same thing as 0, 0, 1, negative 1, 0, 0. Well, we can solve that actually. What we can do is x is going to be equal to y is going to be a free variable. And that means that all the eigenvectors of eigenvalue 1 are of the form t, t. And well, out of this, I can make one independent random, vector. 1, 1 is an eigenvector of lambda 1. I can make only one. Any other eigenvector of lambda 1 will form linearly dependent set. Okay. For lambda equal to 0, on the other hand, we have, well, what? 1 minus 0, 0, 1, 0 minus 0, 0, 0. And if we do a row 2 minus row 1, we get 1, 0, 0, 0, 0, 0. From there, you see that x must be equal to 0, y must be a free variable. So the eigenvectors are going to be 0, t. And well, there will be only one vector out of that, which is eigenvector for lambda 2 equal to 0. Okay. Here, we are working with 2 by 2 matrices. Now, the question is, can I form a basis using eigenvectors? It means that can I find 2 vectors which are linearly independent and all of them are eigenvectors? Yes. You see that 1, 1 and 0, 1 is a basis with eigenvectors. And that is a proof that A is diagonalizable. And A being diagonalizable, what is D? D we already know. Put the eigenvalues on the main diagonal, everything is 0, 0. And the invertible matrix is, well, for 1, this is lambda 1, you use the eigenvector corresponding to that. Put it in the first column. The second eigenvalue is 0 here. I put it in the second place. Then use the eigenvector of that and put it in the second column. That's P. It's easy to check that a P inverse AP is equal to D. So this gives us a criteria and how to make those matrices diagonal matrix and the invertible matrices for diagonalizable matrix.